Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all. This topic on the absorption spectroscopy, which I began in the previous class, let us continue with it. In the previous class, I have already given you the very basic principle of it, and then we went. I also mentioned that the instrumentation part is not important for the chemist. Chemist is more concerned with the spectrum, its interpretation. So let us look at this particular slide on this. So this is one of the spectrum for a real compound. Okay. So what do you see the thing? You have an x-axis, a wavelength which is plotted, and the absorbance on the y-axis. So what are the kinds of characteristics can one derive? So it is not necessary it looks like very so nice, smooth and symmetrical. The spectra can look like this also, as you don't see a very highly symmetric. Kindly look at this particular thing where I am moving. So you have a one band here, and there is kind of a shoulder, there's a major band in shoulder, or you can also have like one band, another band, maybe very weak one, so very strong ones and very weak ones. So there is a combination of different kinds of spectra are possible. So spectra do not mean that always they are very nice, very symmetric, and that is not correct. So when there is not symmetric, that means there is some kind of information is embedded into that. So this embedded information has to be translated. So that's what basically a machine learning kind of thing. So this is what the machine has given, then we have to try to understand that spectrum into the chemical information, and that's what. So we are basically doing a machine learning process, decoding that what we get into a chemically meaningful information. So the spectra to the chemically meaningful. What are the characteristics of this, for example? So number one, if you look at this particular band, you as you keep moving across the x-axis, you would see that it slowly grows up and has somewhere some peak point, and then comes down that you have. So this is what you refer it as the maximum or peak maximum or lambda max. So peak maximum or the lambda max. And then on the other hand, you have here, if you go cut across the y-axis, you will find the absorbance. This is the Amax. So we will come and go through these details a while later in the next slide, but right now let us see the grossly these features. What? So the two things. Anything else then can we get from this? Yes. For example, this width of this peak. The width of this peak is explained as the full width at half maximum. So this is also referred as FWHM. That is also a nature of important. And a shape is a symmetric, less symmetric. As I told you earlier, less symmetric does not mean a bad spectrum. Less symmetric means some information is embedded in that. You will have to reveal that information. You have to unravel that information. So you have to work out. So that is what is an important parameter here. And then the number of bands. Like here, you have so many. They are not just like that. The number of bands will come. So as we keep moving, we will know. So the peak position in terms of the wavelength, and the peak height in terms of the absorbance, and the peak symmetry, and the number of bands. There is one more thing, is their peak width, and also other aspect is to get the quantitation, you can look at the area of the peak. So you have at least several different parameters that I have talked to you. Keep all these in mind all through all the time. Most often we forget all of these and just remember only the peak position alone, and that's not sufficient enough when we are comparing with one reaction with another, when product to another. So you have the peak position in lambda max, absorbance A of A max, these are the two, and then full width at half maximum of the width of the band, then a shape, symmetric, non-symmetric, shoulders, etc., symmetric, non-symmetric, shoulders, etc., and the number of bands. All of these are of course important in a compound. Then area under the peak. So all of these are important for quantification. Most often we use absorbance, but if the band is symmetrically poised, this will give a correct value. Otherwise, you need to look at the area of the peak. So you have 1, 2, 3, 4, 5, 6. So you have all these are characteristics. We call these are all the characteristic features. So if you take two different compounds, not all these 6 will match at all at any given. So of course absorbance, etc., and you may have the match, but not everything, not the width, not the shape, not the number. So these will differ. A huge number of parameters are there in these things. So one can expect the position. This can move greater or lower. Okay. The intensity, it can move upper, increase the intensity, decrease the intensity. So for A max, it can go up, it can go down. Lambda max, it can go higher, it can go lower, and that is what is shown in this particular graph. Here the hypsochromic shift, bathochromic, hyperchromic shift, hyperchromic shift, hypsochromic shift and bathochromic shift. So hypsochromic, bathochromic talks to you in the energy or the wavelength, and the hyper and hypo will talk to you about the intensity. That is the terminology which is used. But otherwise you can always say the band is shifted to higher wavelength, band is shifted to lower wavelength. There is no problem at all. So therefore here the this one, the A max is the one what you are measuring from the spectrum. So this is what you can measure. Of course you can measure the lambda max as well, because from the peak, because that is where making. So this is nothing but epsilon CL, and this epsilon is a very characteristic for that particular group. It is a molar absorptivity. So this is what is characteristic. This is not this one. This one you can change by changing this one, by changing this one you can change this, but it is not that. So epsilon is the characteristic, this is the absorptivity. So you can also use it as a molar absorption coefficient or molar absorptivity. So this is a very characteristic from one group to the other. For example, in organic you will have a COOH group, an NO2 group, or an NH2 group, etc. They will all have different kinds of absorptivities in that. Similarly for inorganic as well. So one can find out this C is your concentration you have used and the path length you have used, because this is where you are using in a cuvette. So the light is passing through, and this is the path length of that light, okay, and whatever the concentration you have taken. So these are the very normal, I'm sure you are aware. And then please practice yourself with respect to the units and other things, which is not easy to talk here. So generally the lambda is talked in terms of nanometer and centimeter inverse. Okay, so energy is talked in terms of the kilocalories and the kilojoules, etc. In those. And in the absorption spectra, they are referred to as the centimeter inverse direction as well. Okay, so whatever we have seen, when a light falls on the cuvette, you take this as your cuvette, you have a sample inside, and you have as if this is a a kind of the particle or a material or something is not that big as you seeing that, just to show shown. So when the light falls on this, there can be a reflection at the surface, and the light can pass through, light can be absorbed, and then light can come out of that, emerging light of that, and the species inside can also scatter. So the scattered radiations will also have in that, the reflections will have, they all will influence the light that is coming out. So therefore you will have certain levels of the errors inbuilt, but those can be subtracted out or it can be minimized. All those things are always possible. So in general, when the light incidents on this particular sample, so you can talk in terms of the reflection, passing through, that is absorption, and then the scattering, all of these. So as I mentioned to you, epsilon molar absorption coefficient or molar absorptivity, and the C is concentration, L is the path length. Now coming to the top on this particular slide, you can see the absorbance is nothing but the log term of I naught by I. I naught is your incident radiation strength and I is the emerging or what is coming out. So you can, so that is absorbance is minus of log of T. T is transmittance, A is absorbance. So the transmittance and absorbance are inversely related. So more transmittance, less absorption, more absorption, less transmittance. We talked about the epsilon CL. Any one of these changes, obviously your total absorbance will change, and that is what is shown from this particular graph as a experimental kind of a thing. Let us take one of them, this black one. This is with some system, you do not need to know what compound it is. Its absorptivity is 50 mole inverse centimeter inverse, and the path length is the 10 micrometer that is being used here. Now that is, as you change the concentration of that, you have very little change. But now if I keep the absorptivity same but increase the path length, so from 10 micrometer to 100 micrometer, what did I do? I changed it by 10 times the path length. So this distance is increased by path 10 times. So that is the red line. You please see the in the one, the red line. So you have much more greater absorbance. Now I would keep the path length same as 100 micrometer, but I would increase the absorbance by from 50 to 100 as the twofold, then it is increasing. So either you change the epsilon value changing means what? Changing from one chromophore to the other, changing from one compound to the other. The x-axis C means what? The concentration of the same changing. The L means what? L is referring to the your path length changing. So any of these, either you change the concentration or you change the L or you change the compound itself, your absorbance will be related to that. Now if you look at under certain kinds of conditions, you may find the absorbance versus concentration as a linear, and that is what is basically the Beer's region or Beers-Lambert region, where you can use for the quantification purpose. So if you get a linear region, that means there is no deviations occurring, then any unknown compound absorbance if you measure, and then you can find out the parameters from that. Okay. So so a straight line, obviously what you have is a slope and the intercept. So using the slope and intercept, you can build this particular thing. So it talked about other things like there can always be some kind of a deviations occurring from this kind of a Beers-Lambert law because of something is happening. You are going from a compound from a very highly diluted to a little concentrated or more concentrated. There could be some kind of a aggregation, dissociation, association kind of phenomena. At times at a higher concentration there could be some chemical variation as well, not only speciation, chemical variation, maybe some reaction occurring, a chemical change, a physical change kind of thing, or you can have instrument based ones, okay, depending upon your detector limit, depending upon your the units which will deconvolute like prism, grating, etc., your light, the breaking into individual wavelengths, that resolution also. So that means the light which comes out, if it has got more number of components of lambda, obviously that will be polychromatic. So such kind of a polychromatic will also give multiple absorption values, and the absorption value will get changed. Why? Because you can see that as a wavelength, the absorbance will be different here, will be different here, etc. And if it is single line or if it is a band, so if it is a band, the value will vary. If it is a single line, that means the resolution of your light also makes, and that can lead to either the absorbance is decreasing, the absorbance is increasing kind of things. So decreasing is the negative deviation, increasing is the positive deviation, and what you are looking is it is the ideal one. Okay. So these kind of corrections etc. are already well known, nothing to worry much for the spectral implications and explanations. Only in the quantitative analysis people use this, but these are all very well taken care now by the instruments by making appropriate subtractions of that. So not too much to worry on this aspect of it. Okay, your spectrum do not grossly change, the quantifications would change in that. Okay, now let us come to the arena of our purview is the inorganic, is the transition metal complexes. Okay. So in the transition metal complexes, what do you have? A metal ion and a ligand. Okay. So the ligand is organic, and ligand will have the ligand transitions. So what kind of a ligand transitions you will have? The sigma to sigma star, pi to pi star, sigma to pi star, n to pi star. These are the kinds of things which you see in the organic. And besides that, you would also see for the transition metal, there could be D to D in most of the cases, lanthanides F to F, etc. And then you can also have the ligand to the metal and metal to the ligand itself. And also the ligand transitions in presence of the metal will get influenced, and the metal transitions will get influenced by the ligand. So therefore, you will have the metal based transitions, ligand based transitions, a mix of the ligand with the metal with the ligand, all of these. And the independent intra-ligand transition need not be like a free ligand transitions, can vary because they are already tied to the metal through the bonding. And that is a good parameter, because you can say because of the shift, because of the change in the width or the intensity, you can say that particular ligand is bonded to the metal ion. So that is a good thing. So if it is the same value, you would not have been able to differentiate those which is bonded ligand versus the non-bonded ligand. I hope that is clear. What I am trying to say is ligand has transitions, same transitions will occur in the metal, but with some perturbation because they are bound to the metal. So as a result of that, your ligand orbitals will vary, shift to higher or lower. Based on that, your lambda will change, and their polarizations will change, therefore their intensities will also change. That is a good parameter. What I am saying in that is, now coming to the transition metal, once again, what kind of a transitions are allowed? The azimuthal delta L is equal to 0, not allowed. So what does that mean? What does that mean is the D to D are not allowed ones. Okay, F to F not allowed ones, S to S or not allowed ones. But what is allowed is 1 plus or minus 1. Okay, it does not matter. So that means S to P you can expect, P to D you can expect, and D to F you can expect, etc. And that will be the difference by 1. But if you go to the higher, it becomes 2, but your intensities will become very low. Second part of this is that second part of that is the spin part of it. So one is the this is now what I explained to you is referred as the Laporte, and the other is the spin. The spin what you require, the delta S should be 0. That means the spin difference should be 0. Okay, so that is where spin selection. If it is non-zero, then it is not spin allowed kind of thing. So the transitions can be spin allowed, Laporte allowed, both unallowed. There are 4 possibilities. So, if you say the spin L and S both allowed, that in the other case, so L allowed, S not allowed, then both are allowed, and then S not allowed, L not allowed, S allowed, and both are not allowed. So, not allowed and allowed. Okay. So, there are 4 combinations are there. So, these are the ones is in fact very important. These are very useful also. These things will help us what kind of a transitions are taking place in this. So, from that you can get what the bandit is, what the transition is, that from that you can derive certain information, both qualitative as well as the based on the intensity is quantitative. So, spin forbidden, but can also be seen many times because the spin couples with the orbit. If it is a pure spin, it would not have been. If the spin couples with the orbit, then there is also. So, therefore, even spin forbidden in some cases will also be seen. Similarly, Laporte forbidden can also be seen when we have a symmetry breaking. So, that will happen when during the vibrations, etc. So, therefore, that is called vibronic coupling. So, when we strictly speaking, the spin allowed not allowed should not show the spin component, but they do because of spin orbital. And similarly, the Laporte not allowed should not show any transition, but you see certain level of that because of the vibronic coupling. And this kind of things becomes very strong in the tetrahedral as compared to the octahedral, because tetrahedral are less symmetric than that of the octahedral kind of things. Okay, and you can see what we talked about delta S difference. So, this is the spin forbidden, because if this electron goes here, how can it pair? If this electron goes here, it cannot pair. Similarly, this electron goes here, this electron goes here, it does not pair. So, that is what is called the spin forbidden means. And if you look at here, any one of these electrons, this one can go and pair with this can go and pair with this can go pair with this can go pair with this. So, there are spin allowed kind of things are there. So, spin allowed, spin forbidden. Similarly, all these transitions in the transition metal DD are all Laporte forbidden, because they are all DD transitions, but you see quite a much of that. So, how do we understand these? You can see if they are spin forbidden, and of course, DD already forbidden, then the intensities are much smaller than 1 in this particular unit, decimeter cubed, mole inverse, centimeter inverse. Okay, and if they are Laporte forbidden always, but spin allowed, then it will start gaining intensity. And for a symmetric, centrosymmetric complexes, the intensity will raise by a little bit, but for non-centrosymmetric complexes, the intensity will be raised by the much greater. Okay. So, 1 becomes 10, instead of 10, it will become even 100 to 1000. So, non-centrosymmetric ones will give much greater intensities of this. Okay. And other one is charge transfer. I will explain you just in a while. The charge transfers are much more stronger than the spin forbidden, the Laporte forbidden, or even spin allowed, all those kinds of transitions. Okay. So, the same thing I put in a slightly different way, so that it becomes more effective. For example, spin forbidden, Laporte forbidden manganese hexaaqua 0.1 is the thing. Spin allowed, Laporte forbidden titanium, hexaaqua 3 plus is a D1. So, 1 electron can go easily to the upper, though DD is forbidden, but the spin is allowed. Okay, that is 1, because the symmetric value increases, but not so much. And the same kind of spin allowed in a cobalt tetrachloro complex is become 50, that means much higher, because of the tetrahedral nature is a less symmetric than that of the octahedral. Therefore, as I mentioned earlier, non-symmetric or less symmetric ones will go to a greater intensities. Then both the spin allowed and Lapode allowed kind of things. If you have, then it will go even into the 1000. Now, charge transfer bands can go even beyond. So, what is the charge transfer? So, charge transfer means a charge moving from one center to the other. So, what are the two centers you have? One is the metal, other is the ligand. So, either you can have from ligand to the metal or from metal to the ligand. So, you may say metal is electropositive. How can you can have? You can have. We have already studied earlier in the past that the Lewis acid Lewis base concept case, you can see that the transition of an electron going, which is already paired with a higher energy, can be given. So therefore, they are the Lewis bases, and if they have a empty unoccupied low energy orbitals, they can take the electrons from out. So similarly, if you apply this concept to this, so when you have the ligand having the electron density higher, or electron pair which is in a higher energy, can be given to the low lying empty orbitals of the metal. So that is the ligand to the metal charge transfer. So that will be referred as the ligand to the metal charge transfer. And on the other side, you can speak this is the metal to the ligand charge transfer. This I will be covering soon. So these are another very important things which you would see even if there are no normal transitions found. This is very common when you have a metal and complex is formed. There will be even a very weak level of ligand to metal charge transfer, or weak level of metal to ligand charge transfer, because they are very characteristic of that. So that is how you can make. Let us look at first one is the ligand to metal charge transfer. As I have already mentioned, that the one which is transferring the charge should have a pair of electrons with a higher energy. So if somebody is comfortable with the molecular orbital picture, they can go into this. Otherwise, you don't need to worry about it. You can take the qualitative, which I am explaining already. So you have a pair of electrons with a higher energy orbital. They are there, so they can be given to the metal, and the metal has a low lying empty orbital here. So in such a case, you can see the metal to charge ligand to metal charge transfer. Okay. So how do we know that it is happening? So how do we differentiate this from the normal pi to pi star? So and then these kind of a charge transfer transitions, because you are transferring the charge from the ligand to the metal, and during the transfer then it is exposed to the neighbor, which means vicinity. That means they are dependent on the solvent effect. So we can, or at times I can change. If I guess this particular charge transfer is from this ligand to this metal, then I can change the ligand. So if I change the ligand, that kind of a charge transfer should not be there. That also can make. So variety of ways one can make. Just have a look at this one. The in a typical complex of this is there is one DD transition, there is another DD transition, there is a ligand to metal charge transfer transition kind of things. So similarly here, chromium hexamine complex, there are some bands here which are for the charge transfer. There are some bands here which would come from the other DD and much lower kind of energies. Right now we are not analyzing these ones, though there is some information is written there, you can basically ignore. If you look at these OXO, they are all D0 system, there is no DD transition, but still they show the charge transfer. The charge transfer is coming from the OXO ligand to the metal empty orbital. So and this is a very interesting, because they don't come from all of them in the same. For the chromium, these are all similar complexes, CrO4 2 minus and WO4 2 minus, MOO4 2 minus, all in hexa valency. So this comes here 370 something like that, this comes as around 270, this comes around much less than that. So you can see that. So this is coming from the chromium, this is coming from the tungsten, this is coming from the molybdenum, and then from the tungsten, etc. You can find out all of these. So therefore that means they are very characteristic. So even the charge transfer transitions very characteristic of that. So based on that. So how do you differentiate? For example, how do you differentiate when you have a chromium hexaamine complex versus the chromium pentamine with chloro? So now what you have, instead of one ammonia ligand, you have one chloride ligand. The chloride charge transfer will be different from that of the ammonia. So based on that, you can easily make out. So you can make out that too. So that is how you can easily make out from the absorption spectrum alone. The other aspect is the metal to ligand charge transfer. So now again the same principle, the metal to charge transfer means metal should have an unpaired electron which are sitting in a high energy orbital. The ligand should have the low lying empty orbital. Most often these are pi orbitals, so there could be pi star orbitals of that, but lower energy on the ligand side, and these are on the higher energy. So that means there could be the pi, still the pi type of things, but the electron filled, and that's what. So most often you will find this kind of a diimine ligands favor in the metal, in their metal complexes as the metal to ligand, because they have the low lying empty pi star kind of an orbitals which will accept the electrons in that too. So and not only these kind of things, cyanato kind of things, other thiocarbamato kind of ligands, many other ligands are there, but the metal should be in somewhat in the lower oxidation state, preferably as low as possible. Then it could be 0, it could be even negative, you know that negative oxidation states are also there. In fact, for example, if we take this particular complex on this ruthenium, it's a very important complex whose research has gone over a period of 20, 30, 40 years in the literature, because of during the such charge transfer, the species lives for some microsecond to millisecond. Therefore, one looks for a lot of reactions. They call it as a photophysical, photochemical kind of a reactions. So all those kinds of things are important. So now we have looked at in this particular class what are the parameters that qualify an absorption spectrum, different parameters, etc., and their positional, intensity, area, width, all of these. Then we have looked at different kinds of transitions, the allowed and forbidden, and how the forbidden ones are also allowed, all those things, and then their intensities, and then with respect to transition metal, and then with respect to the charge transfer, the ligand to metal, metal to ligand, etc. And we need to still continue on this now by looking at the example and by analyzing, and we also need to see how diverse these are, the spectra are. As I said, number of bands, width of the band, symmetry of the band, position of the band, all these. So we should look at examples relevant to all of these. Next couple of lectures will be more on applying these basic parameters. Now I would say that the basic parameters we have already learned, that is sufficient enough for this course, not gone into physics, not gone into the instrumentation part, but this keep those parameters in mind when you listen to the next class on this. Thank you very much.